Here's a sample problem from chapter 6, and we're going to use centripetal force and the centripetal acceleration formula to solve for the speed at which this bicycle rider is going around this loop-de-loop. So what's going on here is that the bike rider is going around this circle. So maybe, you know, they're going along here and then they're going around the circle. So the question here is, what's the lowest velocity or speed that the bicycle rider can have at the top in order to not fall down, basically. So normally the case would be that at the top, the forces would be, of course, gravity is always present. And then there would also be the normal force, which you could either draw like, you know, right on top of gravity, or you could draw like, you know, as another force added with gravity. And those both would be adding together to provide the centripetal force that keeps the biker accelerating in a circle. But in this case, we would say that, you know, you get a really large centripetal acceleration when the speed is large. In this case, we're going for a low speed and a low centripetal acceleration. And so we would minimize the force, and then you could imagine that the lowest speed possible would happen maybe when the normal force would go to 0, basically. And then the only force present would be gravity. Of course, you can't get rid of that. So then let's assume now that lowest or least speed means that we have the lowest centripetal acceleration around this circle, and then that means that we've got Fn going to 0. So although the biker is like staying in contact with the circle, the circle isn't actually putting any pressure, so to speak, on the tires of the bike. Okay, so I just zoomed in on this, so we would have a free body diagram of the system, bike plus man, would just show FG, and that's it at the top of the circle. So if we assume that, then we would say that Fg is equal to the weight, and that's also equal to the net force on the system at that moment. And then, so therefore, the weight is equal to the centripetal acceleration. And then we're going to substitute here the equation for centripetal acceleration, which is v squared over r. And we have m on both sides here, so we could divide both sides by m. And we are trying to solve for v, so let's multiply both sides by r. We have, there we go, and then take square root. So then square root of acceleration due to gravity times radius would give us the speed that the cyclist needs to go at in order to stay going in that circle of that radius, which turns out to be, if you calculate that, when you plug in 9.8, 2.7, then you get 5.1 meters per second. Okay.